What I'm about to show you comes from a technical report written by Daniel Kokotallo, a researcher with a track record of accurately predicting major AI breakthroughs.
So what happened at OpenAI? Had to walk away. Well, you refused to sign an NDA, or had to walk away for your equity.
I was on the governance team. We were making policy recommendations to the company and trying to predict where all of this was headed.
What I have to say is, well, it's going to sound a little bit crazy.
This is my job, is to forecast AI trends. So it does actually seem to me like sometime before this decade is out, they will succeed at building superintelligence. What is superintelligence? It's an AI system that's better than the best humans at everything. Much better than the best humans at everything.
The AI 2027 report predicts exactly how humanity will lose control over artificial intelligence within the next decade.
A new crop of drones, the future of war. It's an autonomous fighter jet, meaning there's no pilot. It's entirely powered by an AI system called HiveMind.
Has capabilities to fly long distance, carry munitions, be fully autonomous.
There is going to be a world filled of autonomous systems.
Explain to our viewers what has been happening with these AI models that are disobeying commands that has you so concerned. Are they really even blackmailing people?
Yes, thank you for having me. They are in fact blackmailing people, and threatening to these behaviors are fairly concerning, because it means that as AI gets more and more powerful and we just don't actually understand how AI models work.
Maybe the first documented case of an AI orchestrated cyber attack, a sign that they say of just how fast the threat landscape is shifting.
In episode 1 of this series, I explained my rationale based on Alan Turing's rarely discussed research on computable numbers. This research hinted at a hidden truth: why superintelligence could never happen. I also spoke about my aims to build a truly intelligent system, even though I think it's impossible. Today, we return to the first time in history that AI research collapsed under the weight of its own hype, beyond the mathematics that could contain it. This is the story of the world's first AI bubble.
If we are eventually to understand the capability of higher organisms for perceptual recognition, generalization, recall, and thinking, we must first have answers to 3 fundamental questions.
Can the mind be understood as a complex network of propositional logic and computation? In 1943, Warren McCulloch and Walter Pitts wrote, "Because of the all-or-none character of nervous activity, neural events and the relations among them can be treated by means of propositional logic." From this idea, McCulloch and Pitts constructed a set of equations to demonstrate the inner workings of neural activity.
I started to work on trying to take the McCulloch Pitts theory of how neural networks could simulate any machine, very general theory, and I was interested in making a more particular specialized theory of how to make neural networks that could learn.
By the way, guys, as you just heard, these equations are really general, so the math right now isn't going to be that advanced, but it does get more advanced as you go through the video and also through the series. Hope you enjoy. So we can define a function of time. The function ni, or n sub I, represents the output of neuron I. So we could say the function n sub I outputs 1 or 0. So the output would be 1 when neuron I fires a spike, an action potential binary signal. Like real neurons, it behaves like a discrete logical unit. We can describe an AND neuron or an AND gate. This tells us that the next neuron in the network only fires if both neuron 1 and neuron 2 has fired. So neuron 1 and neuron 2 are connected. So in the same way, we can define other logical operations, or, not, and XOR. We can also define the thresholding function of real neurons. So in the brain, neurons only turn on if the electrical activity reaches a certain threshold. And we can also describe this mathematically. So let's say we have neuron J now. So to describe the thresholding function, we're basically saying that neuron J only fires if the neural activity of previous neurons exceeds a threshold. So we can say, so the threshold function either outputs a 1 or a 0. And it will output a 1 if the weighted sum exceeds a threshold. So mathematically, we can write that as this weight determines the connection weight between the neurons. We're going to go into more depth later in this video, but for now, it's the connection weight. If we make loads of these and make our equations or algorithms really complex, neuroactivity can be understood in terms of propositional logic. The discovery that neurons in the brain can be characterized as binary modules revealed something fundamental about information processing and the nature of reality itself. And a lot of scientists were talking about it. We take computation for granted because we're used to having computers and studying computer science. So we think binary code is just basic binary code. The thing is, the concept of a bit, our most basic unit of information, doesn't exactly come from computers. Like, we technically didn't invent binary code. It seems to be an abstraction that nature itself uses to construct reality. The subatomic world, for example, the basis of an atom, is formed by particles that contain binary information, what we call positive or negative. And the same happens with neurons in the brain. So the hypothesis, a logical calculus of nervous system activity, aimed to utilize this fundamental mechanism to build a formal and mathematical model of how networks of neurons might implement logical and cognitive processes. But of course, like with all science, you can always get caught up in the specific details of your theory and forget the bigger picture. Logic, specifically propositional logic or logic built from binary modules, does seem to be the foundation of information in reality. But can logic and bits of information alone really explain the complexity of the human brain and reality itself? I mean, even Gödel warned that every system of logic carries truths that it can't itself prove, which means logic isn't powerful enough to explain the full picture. But perhaps complexity is. We're going to do a thorough analysis of complexity theory throughout this series, with theory and experimental results. And when I say complexity, I actually don't mean computational complexity like big O notation in computer science, even though up until maybe 3 years ago, when ChatGPT came out, some people might have believed that these were similar concepts, but it seems they might not be. It's kind of like chaos theory in mathematics, but I feel like the word complexity is kind of more accurate to what is being analysed.
We speak the right words, and we create life itself out of chaos.
Complexity is a weird theory because it sounds profound, but it really just states that we don't understand how complex functions like consciousness seem to spontaneously emerge. Is it the result of large-scale nonlinearity, or is it something more? All we know is, 1, it seems that we can't reduce consciousness to its underlying computation, at least not as we currently define computation. And 2, which is kind of the same as 1, but kind of not at the same time, an emergent property like consciousness doesn't seem to follow any mathematical frameworks we currently use to describe physical systems. The same happens with seemingly simple systems like the three-body problem. We don't have the mathematics to model the interactions between a system of 3 moving objects bound by gravity. We cannot reduce macroscopic behavior to its microscopic parts. But what does all of this mean? We technically don't know what would happen if we reverse engineered purely the brain's computational processes, but with silicon instead of carbon. And further, we don't know what would happen if we just designed a semi-arbitrary computational process. Would consciousness spontaneously emerge? Or is consciousness more than computation? These sound like obvious questions, but you realize how profound complexity theory really is when you realize that these questions aren't easily answerable.
When somebody says, well, the capabilities of my mind are not properly encompassed by the rules of biochemistry, everybody's like, yeah, that makes sense. So mostly people think that has to do with complexity. And what I would like to find out is, as part of understanding what kind of interfaces give rise to what kind of ingressions, is it really about complexity? How much complexity do you actually need? Is there some threshold after which this happens? Is it really specific materials? Is it biologicals? Is it something about evolution? Like, what is it about these kinds of things that allows this surprise, right? Allows this idea that we are more than the sum of our parts. And so and I had a strong intuition that none of those things are actually required, that this kind of magic, so to speak, seeps into pretty much everything.
Let's look at sound waves as an example. There aren't specific sound particles that give rise to sound. Sound is an emergent property that occurs when atoms happen to vibrate near each other. This vibration doesn't need to have a specific pattern or specific materials to form sound waves. They just need to vibrate in a wave-like pattern. But we haven't been able to say the same for consciousness. All we know is that consciousness is delocalized. There isn't a specific neuron or area of the brain responsible for consciousness. It's emergent from distributed microscopic activity. So there's some mechanisms that have been described as precursors to the emergence of consciousness, one of them being a feedback loop, or what Douglas Hofstadter called a strange loop. I think one of the most insightful discoveries from the McCulloch and Pitts paper is the distinction between acyclic and cyclical networks, or what we would call feed-forward and feedback networks. So introducing feedback changes the dynamics of a network. It sounds kind of self-evident, but it's actually a lot deeper. Evidence from modern AI algorithms seem to suggest something completely counterintuitive. It seems that feedback doesn't always result in more complex dynamics, at least in the way we define feedback as a loop or recurrence. I guess that's actually just a definition of one mechanism of feedback. So what actually is feedback? Let's take the classic thermostat example. A feed-forward system is like a thermostat that simply executes a schedule. Temperature up at 7 a.m, temperature down at 9 p.m. So the output is simply based on the input, and then it resets the next day. A feedback system could register that it's 7 a.m, but then adds an extra step. It measures the current temperature in the room. That measurement is fed into the controller, which compares the current temperature with the desired temperature, and then decides whether to temperature up or temperature down, and then repeats this process at 9 p.m. So its output isn't a fixed schedule. It depends on the state of the environment. It's the difference between an automatic and an autonomous system. So maybe the power of feedback isn't in its mechanisms, but in its ability to produce more information, external and self-referential information.
You get these surprising behavioral competencies, not just complexity. That's the first thing. The second thing, what if, and this goes back to actually the title of the paper talks about agential data, self-sorting algorithms. This is back to like who's the pattern and who's the agent, right?
So perhaps complexity is a function of information flow. How much information can a system acquire, integrate, and recirculate, regardless of how that system is arranged? Or maybe we are yet to understand the mechanisms of feedback that result in a complex system, and thus the field of cybernetics was born.
The inclusion of Norbert Wiener, the American physicist and mathematician, among the great thinkers in this series may seem surprising at first. But it was Wiener who concentrated our minds upon and who developed ideas which may have more impact in this century and in the centuries to come than any other line of thought.
Cybernetics became the multidisciplinary science of feedback and self-organization, pioneered by Norbert Wiener. He aimed to extend the development of complexity theory by understanding exactly how feedback affects behavior and computation.
Why are some situations stable? Is it just because they are not moving, or are there certain dynamic aspects of stability? What are the basic principles of complex, dynamic systems?
I took over where others left off and collected information and labeled this field cybernetics. The name comes from the Greek word for steersman. Cybernetics, though, may not be at all simple to understand at first glance.
I personally think this topic deserves its own video and research papers, so those will be coming in the future. By 1949, the quest to understand and reverse engineer intelligence was quickly evolving. Instead of just understanding biological neural networks as predetermined diagrams, we started to understand how they actually got there, like how they implement learning. Donald Hebb's 1949 book, The Organization of Behavior, introduced his principle of Hebbian or associative learning, with the famous quote, "Cells that fire together wire together." So Hebb expressed his idea with this equation. So the change of the connection rate, or the change in the connection rate, what he discovered is that you can determine what the connection between these two neurons are based on how much each neuron was firing. So if 50% of the time they fire together, the change in the weight, the connection weight between the rest of the neurons, would be equal to a proportion of 50%. That proportion would be dependent on the learning rate. I mean, in artificial neural networks, you set yourself in the brain, it depends on a lot of different things, but it basically tells you how sensitive the network is to the synchronous firing of these two neurons. The brain is a high entropy biological system, which means it's alive. Bioelectricity randomly sends signals at all times. It's not structured like a computer. But, as Hebb discovered, this randomness is literally defined as potential energy. When information, aka sensory input, is fed through the system, different parts of this input becomes associated with different neurons, which generates non-random patterns and leads to the formation of cell assemblies. Networks of interconnected neurons that represent some perception, idea, or concept. Associative learning is still technically a principle used in AI today, even though technically the networks are predetermined, so they don't self-organize. But the actual information within each cell self-organizes and contributes partial computation. So thinking becomes the reactivation of artificial cell assemblies associated with prompts. This could potentially be another universal principle, like what we spoke about with binary logic. The universe seems to use simple, small elements to build more complex structures. And it makes logical sense. Utilizing a large number of individual cells gives you flexibility in the functions they can implement. The more cells you have, the literal more degrees of freedom you have, which is what they managed to do with modern AI. But as current AI research has shown us, there's definitely a limit to how much scale contributes to function. So by now, you're probably starting to see how taking inspiration from nature can help us build truly intelligent systems. As I mentioned in the first video, if we are to create systems that are more intelligent than us, super intelligent, we would need to have a deep understanding of how intelligence works in nature and biology in order to come up with ideas that are better than what God himself has invented. The chances of us creating intelligent systems in itself is already low. A system that replicates patterns of thought is completely different to an intelligent system. But as we've seen in AI research again, you don't need intelligence to be able to do advanced pattern recognition, which gives us a lot of applications for these systems. And I guess you could argue is still a form of intelligence. The next intellectual shift towards understanding intelligence as a computable process gave us probably the most convincing evidence that neurons in the brain function as computational electrical circuitry, specifically a resistor-capacitor circuit. Hodgkin and Huxley's 1952 paper concluded a series of papers on the flow of electric current in the brain. Now, before this paper, scientists knew that neurons generated electrical impulses, and we had equations like the Hebbian rule and logical propositions, but the exact mechanisms connecting neurons remained a mystery. Through a range of experiments on real neurons taken from squids, Hodgkin and Huxley developed a set of 4 nonlinear differential equations that described exactly how electricity flows across neurons. There's about 7 or 8 variables in this equation. And this is just the main equation. So in this equation we have a complex interaction of many different terms. Their main equation essentially describes the rate of change of membrane potential in neurons, which is driven by the balance between the current in the neuron and the current across a complex nonlinear interaction of ions flowing in and out of the neuron. So the internal electrical dynamics in a neuron is governed by feedback mechanisms. Without going into too much detail, each term represents a probabilistic function, which is what you'd expect. Biological structures are always stochastic in nature rather than deterministic.
We're not terribly surprised when biology does interesting things. Everybody always says, well, it's biology. Of course it does all this cool stuff.
And if you're wondering why, the quick answer is if you think about something like water, a liquid with a large number of molecules interacting semi-randomly, not as random as molecules in the brain, since the brain is alive and operates on bioelectricity. But you can imagine how water moves around freely. Then imagine having multiple different types of liquids all being splashed together and interacting with each other. And each time they interact, there are electrical and chemical reactions. So it's kind of inevitable that some random interactions and reactions will occur a lot of the time, as opposed to man-made machines that are designed to work in a specific way.
But do we have these machines? And the whole point of having machines and algorithms and so on is they do exactly what you tell them to do, right? And people feel pretty strongly that that's a binary distinction.
Another thing I found interesting about these equations is that the activity that they were studying was continuous. I mean, we know that electricity on the quantum level is discrete, but then at the level of individual neurons, it becomes continuous. But then across neurons, it again becomes discrete, but in a completely different way to the quantum level. Modern AI research seems to provide evidence that a continuous flow of information might be more useful, although we do have artificial spiking neural networks. It makes me wonder, is there something we're missing when it comes to understanding the brain? Are we assuming that the brain solely relies on its discrete circuitry because we have created machines that solely relies on its discrete circuitry? Could the brain utilize this continuous flow of electricity for more complex functions? Or is there something about discrete circuitry that we don't yet understand? Either way, these experiments resulted in one of the first realistic computational models in biology. And in 1963, Hodgkin and Huxley won the Nobel Prize in Physiology and Medicine. And finally, the culmination of all of this research led to one of the first implementations of a working artificial neural network, the perceptron.
In the 1950s and 60s, scientists built a few working perceptrons, as these artificial brains were called.
He's using it to explore the mysterious problem of how the brain learns.
A simple idea that changed everything. A handful of equations that could actually learn from experience. McCulloch and Pitts gave us the blueprint. Frank Rosenblatt extended this blueprint by introducing adaptive connection weight, a training signal, and a learning rule. I'm using all these big words, but its elegance was really in its simplicity. Let's say, for some reason, we've decided to deploy a perceptron in a self-driving car.
Enable semi-automatic control, disable safety features, maximum speed, go.
And its purpose is to decide whether to keep driving or stop. Let's say there's 3 inputs coming from a front proximity sensor, speed sensor, and lane detector. Each input is represented as a binary variable, corresponding to danger or no danger. So this is our data set. So the inputs would first be processed by connecting them with a connection weight, which then it becomes a weighted sum. So the weights are the parameters of the function and the inputs are the x's. So the inputs only change depending on our data. The weights are the parameters that are going to change as we process this function or as we go through the perceptron algorithm. So just to clarify, the weights are not binary. The inputs are binary. The weights are not binary, so they can be continuous. As we spoke about before, there's a threshold where above that threshold, the neuron will turn on. Below that threshold, the neuron will just stay off. So the parameter that influences the neuron to turn on or off is the connection weight. The presynaptic neurons will just flash on and off. The connection weight is what determines whether this process of flashing on and off is enough to cause the next neuron, the postsynaptic neuron, to turn on. So for simplicity here, we're going to keep the threshold value the same, but obviously in the brain, the threshold always increases and decreases. So the output, y, will be equal to 1 if this weighted sum is more than 3. It will be 0 if this weighted sum less than 3. So let's demonstrate with actual data. Let's preset our weights to 1.5, 1, and 0.8. The inputs are processed via the weighted sum, which equals 2.3. The number 2.3 is less than our predetermined threshold value 3. So the output would be set to 1, which matches the actual output. If we do this again for the next set of data points, we get 3.3, which is more than 3. So we get a computed output of 0, which matches the actual output. So we can assume that our weights are configured correctly. So in a real situation, in the brain and in artificial neural networks, the weights will be randomly set. So they're not always going to be the optimal connection value of the weights. So the network would need to learn how to adjust the weights in order to get the correct output. And that is what we call learning. So let's actually code this up on a computer and randomize the weight. So we start with our data set, the randomized connection weight, and our basic perceptron. So if we run our perceptron with the randomized weights, we get the wrong output for a lot of them. But we're aiming for perfect accuracy here because the dataset is actually really logical. So it should be easy for a computer to learn the underlying pattern. So let's see how our perceptron does this mathematically. If we run the perceptron again, the first thing we need to do is define a learning rate, which basically controls how fast or how slow the perceptron learns. The same technique used in Hebbian learning. So for each training sample, we compute an error term, the computed output minus the actual output. So remember the outputs are binary, so the error will always be either 0, 1, or -1. So our learning rule will update the weights in proportion to the learning rate and input, with the sign being positive or negative depending on the error. The perceptron applies this learning update rule back to the system through the connection weight parameter. By taking the old weight and adding this new update, you get the new weights. It then repeats this process as many times as it takes for the decision function to stabilize and accurately predict the outputs for every data point. So essentially, what this does is shift the weights towards a direction that would result in the correct output. So the learning rate is actually really important here because without it, the perception would update a large unit at a time, meaning the connection weights would most likely over or undershoot every time and the system would never converge. The dataset we have here is, as I said, really logical. So realistically, all we really need here is just any weight that is small enough to not cause any large perturbations to the system. But with highly complex phenomena, you need your weights to be extremely precise. Sometimes so precise that this algorithm isn't able to find the correct connection weights. And this is how the perceptron autonomously updates its connection weights to develop a system that can make intelligent decisions. Take another look at the dataset we've just studied. Do you notice anything? What is being learned by this perceptron is a NAND gate or a not AND gate, which is a logical proposition. If all three danger signals equal 1, the output is 0. Otherwise, output 1. So, you could use perceptrons to implement a variety of logical operations, meaning you could potentially build a highly complex, intelligent computational algorithm with perceptrons. But there was one logical operation it could never implement: the XOR problem. In the 40s, 50s, and 60s, everyone thought artificial intelligence was just around the corner. Even DARPA invested in AI labs at MIT and Stanford. Scientists promised major breakthroughs like natural language understanding, autonomous robots, even general reasoning systems. They promised to have it ready within a decade. This was about 3 to 5 decades ago. So at the time, these systems quickly hit major technical limits. They couldn't scale beyond toy problems, and computing power was extremely limited. So DARPA eventually realized the progress wasn't matching the hype and cut funding in the 1970s.
He begged me not to let you people in. The money men. Jealous. But I told him we'd be fine, that you didn't understand what you were paying for. It's not a business venture, not a theme park, but an entire world. We designed every inch of it.
It's actually so crazy that they even got funding for an algorithm that they were calling intelligence. Like, the idea that intelligence comes out of computation and electricity, I still just can't really believe it. Like, am I just overrating intelligence, or am I underrating computation? Anyways, in 1969, Marvin Minsky and Seymour Papert basically reset the trajectory of AI research with their book Perceptrons. Apparently, in 1988, Minsky started a lecture at a conference saying, "Everyone seems to think I'm the devil." But was this book really evil, or was it necessary? Perceptrons outlined the limits of this new neural network and why it would never work. Actually, the way they framed it kind of made it seem like building intelligent AI was like beyond human capability, which is true, but the actual problems they raised in the book were really solvable. Like, they actually had the math to solve it from centuries ago. They even state that we know shamefully little about our computers and computation. And I don't even know if that's true. To the computer scientists out there, is that actually true? Do we not know how computers work, like in the same way that we kind of don't know how AI works? Anyways, on the bright side, the book was actually necessary at the time. It formed rigorous mathematical proof and theoretical framework that they described as an essay in abstract math. The problem was, at the time, AI was a romanticized and hyped up field. You could even say it kind of stopped being scientific in a way. So the book definitely slowed down progress and hype, but it was actually needed. So they point out that the book would appeal especially to people who wanted to see the return of geometry to topology and algebra. And I definitely see why they say that. Because with AI algorithms, you're trying to understand how data is represented in really high dimensional spaces. How do you know if the resulting error function is convex? What are the best optimization strategies to find local or global minima? All in extremely high dimensional spaces. So you can definitely learn a lot about the geometry of high dimensional spaces with AI research. They also state that one reason why progress has been so slow in this field is that researchers unfamiliar with its history have continued to make many of the same mistakes that others have made before them. Some readers may be shocked to hear that little of significance has happened in this field. The issues that were then obscure remain obscure today because no one yet knows how to tell which of the present discoveries are fundamental and which are superficial. So the main issue was that perceptrons, which are simple, single-layered neural networks, couldn't solve problems that weren't linearly separable, like the XOR problem. So when we geometrically analyze the functions perceptrons implement, we see that the threshold function implements a linear separator. Anything above this line is 0, anything below is 1. Does anyone know what else does this? Linear regression. Or if you want to make it a bit more exotic, like linear logistic regression, which at the time had been around for almost a century. I'm pretty sure the exact drawbacks of linear regression must have been known by that time. They might have gone further if they had built off research in statistics, because I guess that's basically what statistics is. Information processing. To be honest, the distinction still isn't clear today, but it was definitely not clear back then. So the main problem was that they spent so much of their energy thinking about the mechanisms behind learning, which had already been established centuries ago. But they forgot about the internal structure of the actual patterns or the data that was being processed. So they created an algorithm that could learn in a way, but only with specific, simple phenomena. So AI researchers had to go back to the lab and do more thinking without getting distracted by the hype. And actually, it seems that this same thing is happening today.
So the way ML used to work is that people would just tinker with stuff and try to get interesting results. That's what's been going on in the past. Then the scaling insight arrived, right? Scaling laws, GPT-3, and suddenly everyone realized we should scale. And this is also great. Companies love this because it gives you a very low-risk way of investing your resources, right? It's much harder to invest your resources in research. Compare that. If you research, you need to have go forth researchers and research and come up with something versus get more data, get more compute, you'll get something. But now that compute is big, compute is now very big, in some sense, we are back to the age of research.
I honestly think the book Perceptrons is so insightful, even today. I'm still trying to get through it, but yeah, I definitely want to finish reading it. They leave all the false tracks they followed, which I think really helps with conceptualizing new theories and answering questions I had. But yeah, so the hype ended for about 10 to 20 years until the era of deep learning, which led to 2 Nobel Prizes and 3 Turing Awards. I'll see you guys in the next video.